All right, let's get the science cart back a little bit. I'm hoping to have a little chat about differentiation and integration, and this video is really made for students who hope to get to calculus at some point. I firmly believe that these concepts should be presented earlier than when you get there, because if you're anything like me and you don't have them presented, then those concepts are very hard to understand. I remember seeing a YouTube video of Neil deGrasse Tyson, one of the sharper tacks out there. And he struggled first couple of months, he said, with calculus. Right? I don't think that necessarily has to be the case. All right, I think the average student starts to drop out at that level because I understand what's going on. And I know I took 3 calculus classes, and none of what I'm about to show you was ever shown to me. And it wasn't until I started doing this that I understood what I was looking at. So this is for you Algebra 1 students. And I strongly suggest you look at it and don't worry about learning it right now. Just plant the seed and maybe come back and look at it again, another day. Plant the seed some more. And usually if you do that 4 days in a row, some of this might start to make some sense. And I think that's really important before you get to a formal calculus class. Okay, because math is a language. You want to be able to speak it. All right, so we'll have at it. And I did put some things on the board. I have not spelled out exactly what I want to say. So we'll just run with it, see what happens. So I've got a picture. Pictures are worth 1,000 words. I've got a square. I used the marker, 1 unit. Over here, I'm a little off, but tried to make a 2 by 2. Right? And 1 by 1 certainly gets us 1 unit of area, and 2 by 2 gets us 4. All right. And we know that when we graph x squared, we get a parabola, right? Where 1 unit squared is 1, 2 is 4, 3 is 9, and the same thing with the negative numbers. And the issue here is we want to talk about change. That's what Algebra 1 is about, right? Changing y over changing x. Except that this isn't linear. So how do we measure that change? Well, we are going from a 1 to a 4. And if I want to add area to this, I can use the marker. Let's say it was all colored in. I could use the marker and go across the board and down. And I have just added a layer of area. And that to me is what a derivative is. It is the amount of area that I just drew there is a little change in the area. And it comes from what? The width of this line segment. Why don't we call it 0.01? So I have that times the length 1, because this is a 1v1, right? And that gives me a little strip of area. All right, and then I could do the other side to maintain the shape. I'll get a little width here, and that width is 0.01 times this length. I capture it there, and then there's a little cusp, that corner, right? Which is actually throwing the calculation off just by a little bit. But such a small little bit, and we're going to look at extending those decimals to 0.01 later, so we get more accuracy. And what would happen? What would happen if I continued to do that? Layer after layer after layer. Right now, I might be at 1.005. I forgot what I was adding up here, but little layer, little layer, little layer, little layer. I kept doing that. I hope you can see that this area becomes the 2 by 2 eventually. And of course, we have a lot of square areas accumulating until we get there. Okay? And so what integration is adding up each of those layers. Now, this is a 1 by 1, and this is a 2 by 2. So generically, what do I have? X times x. So when I have a little change in x times x, I really have a width times a length, giving me these areas, which are rectangular. Okay? So if I started here, I don't know if you can see it, but there's a square here, square area. No, it's 0.001 squared. You can see it, right? It's right there. Oh, we having trouble seeing it? Well, I'll get the next biggest one, the next biggest one, next biggest one, next biggest one, next biggest one, next biggest one. And I continue to just layer this. And each width is 0.001, 0.001. And if I wanted to draw the next layer of area in the same amount of time, my hand's speeding up. The rate at which I'm adding, is absolutely connected to what? Absolutely connected to the length of the side of the square. All right, we'll come back to that in a minute. Let's do some numerical work. See some of the numbers crunched, user-friendly numbers. All right, can we see the first one? Yes. If I square 1.01, I get 1.0201. And if I just take the first two decimals, then this is changing at 2 to 1 when x is 1. Let's look at 2 by 2. And let's increase our, let's let's make our width smaller. Okay, kind of came out there. Maybe another coffee needed. 2 squared is 4. 2.001 squared is, and I'm not using a calculator because I see the patterns, 0.004001. And 0.000001 is the error, that cusp right there. And I think we can pretty much ignore it and look at 0.004 divided by 0.01, which means when x is 2, the quadratic is going up at that instant at 4 to 1. And this is just algebra 1. This is y2 minus y1, x2 minus x1. That's all we're doing. So now I got 4 decimal places. Oh, 0.006. When x is 3, I'm going up at 6 to 1. Math is all about patterns. Let's do one more. Yep, I think you can see it. I'll go to 4.00001, square it, 16.00008, 00001. I think we can ignore that, and we can look at 0.08 divided by 0.001. And yes, at 4, you're going up at 8 to 1. So let's just try to show that. It's hard to show 2 to 1 with any accuracy here, but let's just say that that represents going up at 2 to 1 when x is at 1 for a side length and 1 for an area. I'm going up at 2 to 1, and then at 2, let's say that. So then at 2, I'm going up at 4 to 1, and then at 3, I'm going up at 6 to 1. And can you start to see the right-hand branch of a quadratic? And what's a quadratic? That's the square area, and doubling that tells you at what rate you're traveling numerically up in your table. And then I should have done this on the computer, what that one is, and then what that one is. I'm going up by 0.001, and that's all about the next layer, the next layer, the next layer. I'm going up by 0.00, numbers like that, which in calculus becomes the term dx. It's a concept. You can think of dx as change in x. So how do we add things up? I think Leibniz coined, with a colleague, coined it integration. I think Leibniz wanted to call it some kind of Latin term, summariano, something about sums, right? And they use this symbol. That looks like an S in the word sum, right? And if you were to add up the layers from 1 to 2 of the multiplication of 2x dx, you actually get x squared from 1 to 2. All right, x squared is 4 minus 1, which is 3, which I'm going to show you graphically now. All right, and that's the fundamental theorem of calculus. Each function has its signature rate of change. And I think I'll expose you to some of those. The cubic will be the next one that we look at, and sinusoids later on in the term, just to give you a little feel for the layering process involved. And keep in mind that maybe the x-axis is a timeline. Okay, so this is time. And maybe 2x represents a rate at which something's happening. And this is multiplication. What's rate times time? Amounts. right? So that's area that we're getting, right? Length times width is area. All right, what area is it? Okay, well, here we have it. I'm gonna actually look at it now. All right, here's the 1v1. Okay, and 1 times 1 is 2. And if I swing this up, this arm up, right, I get 2 units when x is 1. Right, and if I swing the 2 by 2 up, I get 4 units when x is 2. 1 gets me 2 units of change, 2 gets me 4. And if you said, oh, that's the graph of y equals 2x, well, I got to make sure I hit it properly. There's 1, there's 2, okay? Y equals 2x, then this becomes a rate function. Oh, God, I didn't do it such a very good job. Rotator cuff problems. Let's try to do that better. All right, 1, 2, and I'm going to finish up here very soon. Let's try this again. That's a little better. Oh, still a problem with the rotator cuff. All right, so I'm actually going to do a layer. Boom, boom. But I'm going to take this layer and swing it up. And it becomes 2 units. So that is going to be my first layer here. All right, and I'm just going to keep doing it until I get to the 2 by 2. Each one, right? Every time I do one, it's a layer and a layer and a layer and a layer. And the smaller the width, the more accuracy I'm going to get. Conceptual. And let's just look at what we get for area here. If I go to 2, 1, 2, 3, 4, I'm up here somewhere, okay? All right, so x value of 2 gets me a 4-to-1 ratio of change. Up here, 2 times 1 gets me 2-to-1 ratio of change. And what do I get? If I look at the area of rate times time and amount, each one of these layers represents one of those amounts, one of those layers of change. Okay, and we're taking a microscope to it. All right, so what's the trapezoidal rule? Width divided by 2 times the altitude on the left plus the altitude on the right. Let's do it. What is the width from 1 to 2? 1 unit divided by 2. What is the altitude on the left? 2. What is the altitude on the right? 4. And those are rates. Okay, and what's 6 times a half? 3. All right, and you tell me the change in area when x is 1 for x squared is 1 unit of area. For 2 squared is 4 units of area. And what's 4 minus 1? 3. All right, and I just wanted to plant the seed right there for what integration is. Integration is the adding up. Did I actually do the fundamental theorem? I think I did, but one more time. 2x dx equals x squared, which is often referred to as the parent function, and 2x is a little f to distinguish between the amount function and the rate function. And we measure from 1 to 2, which means I'm doing x squared for 2 minus x squared for 1. And that's measuring the area under a curve, which means we can use any curve. Start measuring the area under it if we can find the patterns to how it accumulates. Okay? Then if you know the rate of something, now grandma's on Route 91. She's driving at a consistent rate of 50 miles an hour. She's at mile marker 3 right now. An hour from now, where will she be? Mile marker 53. Okay, grandma's okay. She's driving 50, but we study math in case she goes down to like 10 or 15 miles an hour on Route 91. So if anybody ever asks you why you study math, it's to save grandma. All right, of course, now I'm grandpa. All right, we'll see you in class. I suggest you look at this 3 or 4 times before you get to calculus. Oh, I talk about it in more detail in the video. What's the relationship between differentiation and integration? Might be helpful. All right, good luck to you.